Today we're going to talk about SciMath again. This is the third lecture on this subject, and today we're going to do some new things. We're going to discuss, first of all, precision in science. So let's consider we have two electronic balances. If you've ever walked into a grocery store and noticed the scale they have in the vegetable department, you can put a few things in there and get an approximate weight. But if you go to the deli and measure something, the delicatessen will probably measure things much more precisely because their scale is more precise than that hanging basket scale in the produce department. Well, it's the same in the lab. We have an electronic scale. In the laboratory, I have one that measures grams with one decimal place. So 2.4 grams, 3.6 grams, 100.2 grams. And I have another one that measures 3 decimal places. The scale that measures 3 decimal places is much more precise. It is so sensitive, so precise that when we're using it, you have to turn off the air conditioner or any fans in the room because it will affect the measurement. There's a little dome-shaped plastic covering that keeps the air from blowing on it to try to get a very precise measurement. So, precision, which one? An electronic balance with more precision would have many more decimal places in its measurement. Let's talk about liquid measure. If I were using a beaker or a graduated cylinder to measure out some water, the beaker, if you haven't seen one of those, then look up an image online for each of these. But a beaker looks just like a glass, and it has maybe 5 markings on it. And each marking is about a half cup, 100 milliliters. A graduated cylinder has something called graduations on it. Those are the tiny little markings up the side of the cylinder, and each one measures 1/1000th of a liter instead of 1/10 of a liter. It's much more precise. And if we are in class, remind me when the video is over and I will go and get one of each and we can look at those and compare them. So I'm going to talk about accuracy and precision. We're going to talk about sig figs. And in the next video, we'll talk about mathematical operations and scientific notation and relationships of inverse and directly proportional. So in this video, we're going to focus on the first two. Okay, accuracy versus precision. Accuracy is talking about how close measurements are to an accepted value. If you know, let's say that you wear a size 6 shoe and you go to a store and one shoe you try on says it's size 6 and it's too tight, and the next shoe you try on says it's size 6 and it fits perfect, and the third shoe you try on says it's a size 6 and it's too big. Those are not very precise. Those are not very accurate measurements. Accuracy is near what is an accepted value. Precision, though, if every shoe you tried on fit exactly the same, then the measurement of that size shoe is precise. There's an illustration on the next slide that I think is going to make this more clear. Imagine you're playing darts and you have a dartboard and you throw the darts. Where is it you're trying to get the highest score? Well, in the center, on what's called the bullseye. So in this first picture, all 4 darts that were thrown landed in the bullseye. It is very accurate. It is right where we want it to be. But it's also precise because each of these darts landed nearly the same place. Let's look at the second picture. This is also precise. Whoever threw these darts was very precise in their hitting the dartboard. They hit at the same spot. It was precisely away from the center, but it was precise. So accuracy would be if you hit the target. Precision has to do with doing something over and over and over again. Here, these are sort of random. They're not precise, and they're not accurate. So we say there's low accuracy and low precision. Okay, there's a topic called percentage error. Percentage error is a calculation. It is how do we describe how far off we are from where we want to be. We're doing measurements. How far off are we? And there's a formula, and it looks like this. The top part of this formula is the error. This is what we measure. This is what we believe the value should be. Let's say you're going to the doctor and you normally weigh 110 pounds and you get on the scale and it says you weigh 120. Immediately you would say, I'm 10 pounds off. So that's an error. Well, if you divided that by the weight that you believe you should be, you would be calculating the percent error. This is a great video. We're not going to watch it right now in class. This is something you can watch at home, but this gentleman, Tyler DeWitt, I've mentioned him before. He has the most informative videos on chemistry, I think. So you're going to look up this title, Error and Percent Error, and Tyler DeWitt, and you can watch this video. He does a great job. The only difference in his video is that in this calculation, he takes, instead of just subtracting the error, he takes an absolute value. But if I go back quickly and look at this formula, sometimes it's important to know if your error is below the accepted value or above the accepted value. So our book and myself, I like to keep the negative or positive number when you're doing percentage error. It tells you if you undershot or overshot. We have a problem. We're going to stop the video now and you can try to work this problem. A student is in the lab, measures a mass using a scale and a volume of a substance with some sort of a graduated cylinder, I suppose, and then calculates mass over volume, calculates the density. It calculates it as 1.40 grams per milliliter. Well, whatever this substance is, the student looks it up and finds that the correct value should be 1.30. What is the percentage error of this measurement comparing these two values? And I'm going to go ahead and skip the solution because I want you to try to do this one, but it's a quite simple calculation. Well, there's always some reason for errors to happen when we're measuring things. It's humans usually doing it. Maybe it's the skill. If someone's trying to take my blood pressure and they don't understand how to put the blood pressure cuff on my arm, or they put it on my elbow where you can't feel my pulse, their skill is going to give an inaccuracy in the measurement. The conditions of the measurement. Maybe you can't reach what you're trying to measure. Maybe it's hard to measure what you're measuring. Maybe your device isn't working well that day. That's the last point. If your measuring instrument is broken, like I said, if we go to the doctor and suddenly the scale there tells us that we're 10 pounds more than what we expect. Either we've gained weight or someone's scale is wrong, the doctor's or yours at your home. So there are several things that can make measurements be in error. So one of the things that we discuss often is how can we trust numbers? How can we trust numbers that we use in chemistry that we have measured or that someone else has measured? So we look at all of the numbers, the digits that we know. Which ones are we sure about? And then the last one is sometimes estimated. So sig figs is a type of measurement where we know most of the numbers, but the last one we estimate a little bit. So significant in this case does not mean certain. It means we can use our eyes to get to the last significant number. Here's an example. If we have this centimeter ruler and we're trying to measure the length of a nail, the ruler's got lots of small lines on it. So if I look at it in the first picture, it's kind of hard to see where it is. But if I used a magnifying glass, I could see much closer, or at least it would be larger. And I can see that if this is 6 and this is 7 centimeters, then between there are 10 graduations, 10 lines. So I can count where I'm landing. 1, 2, 3. I know it's bigger than 6.3, but the tip of the nail is not as far as 6.4. So I could say 6.3 or 6.4, but that wouldn't be showing all I know. I can guess that we're between these two, and I can say 6.35. If I could tell that we were much closer to the line on the left, I might have guessed 6.32 or 6.33, and so on. So the last number we estimate. We can't see a line to tell us the last number, but we kind of guess. And that's still significant because we're using our eyes to guess the last number. There are lots of rules to describe how we would determine which numbers were significant in a measurement. Just what we were talking about now, we would be given a number, but if we saw a number written down, we wouldn't know what sort of measurement device was used, so we'd have to decide that. And here's some of the rules. Biggest rule that's not listed here is that any number that's not a 0, that particular digit is significant. But it's the zeros that are tricky. So if we have a 0 that's between two non-zero numbers, so a 0 that's sandwiched in between. You see here, this 4 and this 7, there's a 0 stuck between them. That means that all three of those numbers are significant. That 0 is significant because of its position between two non-zero numbers. Same thing here. That 0 and that 0 both are significant because there's a non-zero after it and a non-zero before it. When it starts to get tricky is the ones that are in the front, like this, 0.0009 kilograms. These zeros right here are not significant. They're called placeholders. They're just showing us where that 9 should be. And you might remember, if you write this number in scientific notation, you would just write 9 times 10 to the minus 4. All those zeros would go away when we wrote it in scientific notation, because they really are just telling us how small that 9 is, how far away from the decimal the 9 is. And this number, all of these would be significant, but these two zeros in the front would not. So this number we would write in scientific notation, 9.5897 times 10 to the minus 2. Again, those zeros disappear because they're not significant. On the other hand, if the zeros are at the end of the number and the number has a decimal, as long as there's a non-zero number in front, then any zeros behind the decimal are significant. See this number 10 right here? It only has one significant figure because there's no decimal there. So that 0 in the back is not significant because there's no decimal. It doesn't mean that the value isn't 10. It just means that only the 1 is of great importance in the calculation. Here, all those zeros count because there's a decimal and a non-zero number. So the last one here explains what happens with zeros at the end. And I gave you an example with this number 10. Here, 2000. I don't know if somebody was counting bags of 1,000 marbles and they just had 2 of them. And they might not really be sure if every bag exactly has 1,000 marbles. Maybe one bag has 998. So it's not very accurate. So we would say this number has only one sig fig. And if we were going to write it in scientific notation, we would write 2 times 10 to the third, which is 1,000. 2 times 1,000. 1 sig fig. But look here. This 2,000 does have a decimal. Someone measured it to the ones place. Someone measured 1,999 and then got to 2,000 exactly. That number says 2,000 exactly. It wasn't 1999. It wasn't 2001. It was exactly 2,000. So those are some of the rules and show you how and what significant figures mean. And there's a sample problem. How many sig figs are in each of the following measurements? So I want you to do these as well in your notebook. So you need to pause the video here, write down these numbers, and then determine 1, how many sig figs are in each, and 2, which of these rules did you use to determine the sig figs? You may need 2 rules to do some of them. Okay, I think we are going to stop right